I'm Ted Berge. I'm with CGG, and what I'd like to share with you today is the results of a system profiling study that's been kind of ad hoc, going on about 3 years, and the impact that has had on our system design point, if you will. So the net of it is pretty simple. What the profiling data has shown is that we can move from a kind of a one-size-fits-all design point or worst-case design point so that every piece of equipment can handle the worst-case job requirements to something that's more like a mean plus one standard deviation. All right, so to start, I'd like to tell you a little bit about the CGG Data Center. Conceptually, I view it as consisting of three main parts. There's the seismic operating system, the storage subsystem, which we refer to as storage islands, and then the compute subsystem, which has both CPU and GPU parts. The seismic operating system is basically a whole bunch of CGG proprietary software, and fundamentally it does data and job management. So it's orchestrating data flows and scheduling jobs. The storage islands are sort of very simple commodity building blocks. It's basically a Unix host, 10 gigabit network connected with direct attached drive arrays, typically 250 terabytes raw. We have several hundred of those in total. I/O is actually served off of these via I/O proxies that run on the host. There's probably 20 petabytes total as a ballpark number for the data center here in Houston. The CPU compute nodes are just straight commodity x86 gigabit Ethernet connected, rotating drives for scratch space. There's maybe 2 petaflops worth of those in total. And the GPU compute nodes, the key thing there is that we've got quite a bit of SSDs on those for scratch. It's the only thing that'll keep up with those GPUs. And ballpark, that's about 20 petaflops single precision here in Houston. So the way a job works at a very high level is once it's launched on a compute node, the compute node will contact the Seismic OS to find out where its data sets are, where they reside. The compute node will then talk to the appropriate storage island. The input data sets for any given job can be spread across 10, 20 or more of these storage islands. All right, so what I'd like to talk about is 2 profiling examples from the storage subsystem and then 2 from the compute subsystem. So to start with, I'd like to talk about just the basic data rate profile off of these storage islands. So this was quite interesting. So what we used was a Monte Carlo method. We're basically looking at proc dis stats. We set up some scripts to randomly sample these storage islands at 5-minute intervals over a 6-month period. We've got tens of thousands of these samples. And basically, we're looking at data rates off the drives and off the network, right? And so what you see over here is a histogram of those samples. We've got fraction of samples. And then here is the data rate off the storage island. Nominal units are megabytes a second, read plus write. I have obfuscated this, all right? So I've scaled that. Think of 1 as the kind of practical peak of any given storage island. So what stands out here to me is that our aggregate load, our mean load across these storage islands is about 1/8 of what they're capable of. So that's something that we can take advantage of. A simple way to do that is we just add more drives to each of these storage islands. We'll bring the disk throughput, network throughput, and CPU resources into better balance, so on and so forth. There is some performance hit for heavily loaded cases. That's to be expected, but we can tolerate that. We run a throughput data center. Savings in terms of dollars per terabytes, maybe 20%. So for us, at least, it was something worth doing. Okay, here's another example from the storage subsystem. So we were interested in what our I/O request sizes looked like. This turned out to be fairly difficult to get a hold of for a variety of reasons. What we ended up doing is using the Linux block layer tracing facility. We can get temporal traces. We have to do a lot of post-processing on that to get what I would call the user level request distribution. And that's what this histogram shows. So this is the fraction of requests in a given bin size, a given bucket size. Nominally, this would have been in kilobytes. Again, I've obfuscated it. So this value of 1 is a request size which represents an approximate break-even point between requests which are seek dominated and those which are bit transfer dominated, right? So these are little small few kilobyte requests. These guys are much, much bigger. A couple of things stand out about this. In terms of the requests themselves, approximately it's a bimodal histogram. We got about half of our requests here are these small IOPS type requests, and the other half are these big, gimme gobs of data, megabytes of data. And then if we look at the actual bytes transferred, it's all up here, right? It's all in these large requests. So this was interesting because it suggested that transitioning to an object store might be feasible, right? So one of the things about object stores, generally speaking, is that they want to deal with multi-megabyte objects. And so we've started to experiment with that. So our fundamental motivation here, as in the first profiling case, is primarily cost. There's some other benefits for object stores, including improved data protection. This is very much a work in progress. We are in advanced testing of a well-known erasure-coded object storage package. We do require a POSIX file system layered on top of it. That's for compatibility with our Seismic operating system. So object stores are a very interesting beast, at least with rotating drives. You'll see much higher latency for individual I/O requests. I've said 5x here, but it's at least 5x, maybe 10x. But one very nice thing for us was we're observing excellent scaling with client load. So we get tons of complaints about hotspots on storage islands or jobs running slow. And we hope that this will alleviate that to some extent. So our current storage islands, hardware RAID-based, obviously give excellent performance at low load, but due to thrashing, performance degrades as client load increases. So this shows you roughly what we've observed for one particular synthetic I/O benchmark. So we've got throughput off of each type of system, one based on hardware RAID, essentially one of our production storage islands, the other an erasure-coded JBOD box. Again, I've obfuscated the scale here, but at very low loads, you can see throughput is poor, corresponding to that much higher latency on individual request. But we do get a nice linear ramp until the drives are saturated. And that performance does hold up very nicely over a range of 4x more client threads. Hardware RAID does about what you expect, right? Performance tails off. All right, so let's switch over to the compute systems and look at GPU systems for starters. So the thing about the GPU systems, at least the ones that we deploy, is they're quite expensive. And it's not just because of the GPUs. The SSDs are quite expensive as well. So what we did in this case for the profiling is we collected statistics based on production job log files. Went in there, pulled the resource usage stats for these jobs. This covers like 9 months worth of production jobs. This will be hundreds of thousands of jobs. And in this case, I'm weighting jobs by their the amount of cluster resources they consume. We call that the node minutes, right? But it's basically GPU cycles being consumed. So what I've got in this histogram is it's a cumulative distribution function of showing the percent of node minutes versus the amount of resources the job required to run, what it actually used. So again, I've obfuscated it. 1 is the largest or most heavily resourced GPU system we've got in the data center. I'm looking at host memory, GPU memory, and then Scratch. These are really SSDs at 100x the scale. So what really stands out here is that 85% of our GPU cycles are consumed by jobs that require only a fifth of the available resources on those nodes. So this one's interesting. Our current GPU system design point is a system, well, our previous design point was a system with 2 GPUs, a lot of memory on each GPU, a lot of memory, and most importantly, a lot of scratch. We've got some jobs that require a lot of scratch space. So the only way we could think to take advantage of this a little bit is we would go with a 4 GPU system with half as much scratch per GPU. So we've got the same total amount of scratch space. But on a per GPU basis, we do save quite a bit. We can still run the very large problems, the ones out here, right? Individual jobs get split across GPUs, but most of our jobs are small and they'll run on a single GPU, and we run 4 in parallel. So this gave us a fairly significant cost savings on the order of 20% again. It did put quite a burden on the software developer who had to implement some of this, so kudos to those people. All right, moving over to the CPU compute. This again follows the theme of scratch space. Very similar kind of method here. It's basically a Monte Carlo profiling method. We're looking at the actual scratch being used on disk for CPU jobs. Basically, we're pulling this out of /proc, and we do a lot of post-processing to get the maximums. So this is the histogram showing percent of jobs and scratch disk use. 1 is the maximum overall in the center. So what's really interesting here is at 1/32nd, namely 3% of the available resource, if we tally up all of these, we get 85% of the jobs need 3% or less of the resource. Now, this is not a big dollar hit, right? We're talking about rotating drives, right? They're dirt cheap. But it's something that we would like to take advantage of. So this one is still very much a work in progress. We haven't actually implemented anything here. We're looking at perhaps a 2-tier scratch design. There are lots of interesting things out there that we may be able to take advantage of. All right, so To summarize, 3-ish years ago, we started profiling various subsystems in our data center, compute and storage. And what it's really done is enabled us to shift the design point of our building block. So we've moved from a worst case design point to something that's more like mean plus 1 sigma. The real advantage there for us is cost. I mean, there are some definite downsides to that. As I mentioned, it does put a lot more burden on programmers in some of these cases. It does put more burden on the sysadmins in some cases. The data center starts to look more heterogeneous. Interestingly enough, it did provide data to kind of give us a push to look at some new technologies. So in particular, the object store. It was that data that gave us the confidence to invest the cycles into that. That's it. Thank you.
Any questions? Kenneth?
On this object store that you just mentioned, you said you created a POSIX compliance layer. Did you have to actually touch the application much?
None.
None at all.
None. And you're referring to our processing modules.
Right, right.
No changes. That's a requirement.
Application wasn't touched. It's just the layer that you created from scratch to be able to connect the file system to the application, correct?
Let's just say there is a POSIX compliant layer there, and that's what our modules talk to. Underneath that is an object store.
Okay.
Thanks very much, Ted.
Thank you.